In this video, we're going to be looking at the mean value theorem and Rolle's theorem. First of all, let's look at Rolle's theorem. Rolle's theorem states, let f be a function that satisfies the following three hypotheses. If f is continuous on the closed interval ab, and if f is differentiable on the open interval ab, and f of a equals f of b, then there is a number c in the interval ab such that f prime of c equals 0. Let's think about this graphically. If we have a continuous function on a closed interval, let's draw a continuous function on a closed interval, and I can see that in criteria number 3, f of a has to equal f of b. So if this is a and this is b, here's a continuous function where f of a equals f of b. So this function is continuous on the closed interval ab and is differentiable on the open interval a to b. And f of a equals f of b. Here we can see f of a equals f of b. The conclusion is then there is a number c in the interval ab such that the derivative at that value will give us a slope of a tangent line that equals 0. And we can see that happens here. Now we do have to be working with a continuous function on the closed interval, because if the function was not continuous, we could have something like this, where this is a and b, and this here was a, and we don't necessarily have to have the slope of a tangent line with this function someplace between a and b, because it's not continuous. Now it says f is differentiable on the open interval, and the reason it's on the open interval, we can't take the derivative at those endpoints. If you think about the derivative comes from taking the limit of f of x minus f of a all over x minus a as x approaches a. And if we try to find the derivative at an endpoint, we'd be looking at the two one-sided limits, and we could approach a from the right, but we couldn't approach a from the left. So we wouldn't be able to find the derivative at that point. And another reason it has to be differentiable on the open interval is, let's say we had a graph that looked like, if we had a graph that was the absolute value, an absolute value graph. If we had something that looked like this. Now, f of a equals f of b. It is continuous, but this is not differentiable on the open interval at c. And we know, because this graph comes to a point, it's not differentiable. Because if we tried to say there's the slope of the tangent line is 0, that's not true. But this function is not differentiable at c. So looking at some graphs to verify this conclusion, even if we have a horizontal line, we would have the slope of the tangent line for any value we chose between a and b, and it still would give us the slope of the tangent line equals 0. So it still works for a horizontal line. Here, if we have an interval a to b, we can see it's a continuous function. It's differentiable on that interval, the open interval, and f of a equals f of b. Therefore, there is some value c such that f prime of c equals 0. Here's another graph. We have the interval a to b. It's a continuous function. It's differentiable. And f of a equals f of b. Notice with this graph, we have two different values that the slope of the tangent line would equal 0. And another graph. We have a continuous function that's differentiable. And that open interval, f of a equals f of b. So between a and b, there has to be some value c such that f prime of c equals 0. A person on a 20-foot cliff throws a ball straight up into the air at a velocity of 64 feet per second. The equation to model the position of the ball at any time is s of t equals negative 16t squared plus 64t plus 20. See the graph below. So here's a representation of the height of the ball. Now this isn't the path of the ball here, it's just the height of the ball with respect to time. The ball is being thrown straight up, it comes straight back down. Show that the velocity of the ball is 0 at some time t between 0 and 4 seconds. Now notice, this isn't asking us to find the value where the velocity of the ball is 0. It says show that the velocity of the ball is 0 at some time between 0 and 4. So we should be able to use Rolle's theorem to show that the velocity of the ball equals 0 on the interval 0 to 4. Now let's look at time equals 0. If we plugged 0 into our function, we would get 20. And if we plugged 4 into our function, you can see we would get 20 also. So we are working with a continuous function. It's a polynomial. Polynomials are differentiable everywhere. And so the criteria for this problem is satisfied. The three criteria we talked about for Rolle's theorem is satisfied. So we should be able to make a conclusion. Since these three criteria are satisfied, the hypotheses, we need to have a value of c such that f prime of c equals 0. Well, what does f prime of c represent? This is the function of s of t. S prime of t would represent the derivative of the function. So that would give us our velocity. So we can see the velocity must equal 0 between 0 and 4 seconds. And if you thought about what's going on with that physically, we are taking a ball, throwing it straight up, and it would stop at its highest point before it started coming back down. It does that within the time interval 0 to 4. Prove that the equation x cubed plus x minus 1 equals 0 has exactly one real root. Now, if we used Rolle's theorem, we could say we're working with a cubic. So the maximum number of times a cubic can cross the x-axis is 3 times. Now this is saying prove that the equation has exactly one real root. If we use the intermediate value theorem, we may be able to show that the graph crosses the x-axis at least once. Let's see if we can do that. To use the intermediate value theorem, we need to be working with a continuous function. This is a continuous function. So we would have to show some value is below the x-axis and then some value is above the x-axis. So if I choose 0 and plug that into the function, I can see I get a negative value. And then if I plug in 1, I would get 1 plus 1 minus 1 is positive 1. So it's above the x-axis. That means between 0 and 1, it does cross the x-axis. So there is one route. Now it could be going the other way. I'm not sure on this one, but it does cross the x-axis between 0 and 1 using the intermediate value theorem. Now, if this graph crosses the x-axis again, it would have to come down, cross the x-axis like this. So could we use Rolle's theorem and say, well, at the x-axis where it crossed the roots, let's call that A, let's call this B. If it does come back down and create another x-intercept, we would have f of A equals f of B. Now, are we working with a continuous function? Yes. Polynomials are continuous and they're differentiable. So those two criteria are met. So this is differentiable on the open interval, and it is continuous function also. So there should, if it does cross the x-axis again, there should be some value c such that f prime of c equals 0. So that would be right in here. So this graph would have to go up, come back down like this to cross the x-intercept again, or have another x-intercept. Well, let's take a look at the derivative of this function. We are working with y equals x cubed plus x minus 1. And the derivative of this function is 3x squared plus 1. Looking at that derivative, this derivative is always positive. That means the function is always increasing. So this cannot happen right here at C. We cannot have a slope of the tangent line that will be 0 between f of A and f of B. Therefore, this graph does not come back down and cross the x-axis again. And we showed that using Rolle's theorem. Now the mean value theorem. The mean value theorem, we have two hypotheses, and then we can state a conclusion if these two hypotheses hold true for a function. So they are, f is a continuous function on the closed interval AB, and f is differentiable on the open interval AB, then there is a number c in the interval AB such that. Now let's think about this graphically. So we are working with a continuous function, and notice this one differs from Rolle's theorem in that f of a doesn't have to equal f of b, but it is a continuous function. So let me just draw a function in there. There's a continuous function on the closed interval, and this would be differentiable on the open interval a to b. Now look at what this is saying. This will help you, this diagram will help you remember Rolle's theorem, the mean value theorem, because this is saying that if we draw the secant line between these 2 points, how would we find the slope of that secant line? This would be f of b minus f of a, all divided by b minus a. That's how we would find the slope of that secant line. Let me draw in a tangent line that is parallel to that secant line. There's a tangent line that's parallel to the secant line. So at that point, f prime of c would equal the slope of the secant line. This is finding the slope of the secant line. This is the slope of the tangent line. If they are parallel, then they are equivalent. So when you think about the mean value theorem, think about this diagram. If you forget the mean value theorem, just think about the slope of the secant line. You know how to find the slope of the secant line, f of b minus f of a divided by b minus a. And then there has to be some value c that we plug into the derivative so that f prime of c equals the slope of the secant line. And if you analyze this a little bit closer, what we have here, do you recognize that if I multiplied both sides by b minus a, we would have f of b minus f of a equals f prime of c times b minus a. And that should look familiar. That looks like the point slope form of a line. Here we have our change in y's. Here we have our change of x's. And here's the slope of the line. Looking at this graphically, as we did on the previous slide, that would be the slope of our secant line. And we have to have a tangent line someplace between a and b that would have the same slope as the secant line. Here's another graph. Notice for this graph, if we looked at the slope of the secant line between a and b, we have several different values of x where the slope of the tangent line would equal the slope of the secant line. So we can get more than one value. And we also would have slope of a tangent line right in here also. Find a number c for the function y equals x cubed minus x on the interval 0 to 2 such that f prime of c equals f of b minus f of a divided by b minus a. if you think back to the mean value theorem, it didn't tell us how to find that value C. It just said that value of C must exist. So the mean value theorem is an existence theorem, which means that C must exist between A and B. Now this problem is actually asking us to find the number C. So here we have our endpoints. Comes from our interval. A is 0, B is 2. Since we're working with a polynomial, we know it's differentiable and continuous for all x. So we could write it in the alternate form and substitute the values. We said B is 2, A is 0, so we'd have 2 minus 0. F prime of C is the slope of the tangent line, but we don't know what the value of C is, so we just leave it as F prime of C. And then we have our function to plug in B. B is 2, so if we plug that into our function, we'd have 2 cubed minus 2, which is 6. And then plug 0 into the function, so we would get 6 minus 0. Now if we divided both sides by 2, we see that F prime of C equals 3. Well, what does F prime of C mean? F prime is the derivative of our function evaluated at C. So if we took the derivative of our function, we would get 3x squared minus 1. And then we plug C in for our x's to get 3c squared minus 1. And then we can set 3c squared minus 1 equal to 3 and solve for C. So when we solve for C, we would get plus or minus 2 over the square root of 3. But the negative 2 over the square root of 3 doesn't fall within the interval, so we only choose 2 over the square root of 3. And this graph is just going to take us through what we just found. There's our interval from 0 to 2. There's the secant line between those two values. So we can calculate the slope of the secant line. We got 3. We know someplace between 0 and 2, the slope of the tangent line would have to equal 3. And we found that to be 2 divided by the square root of 3. If we plugged in 2 divided by the square root of 3 back into our derivative, we see that the slope of the tangent line is 3 at that value of x. Here's an example. You pass a policeman in your car at mile marker 1, and 4 minutes later pass another policeman at mile marker 6. The speed limit on the highway is 65 miles per hour. You saw the police at the first mile marker and you slowed to 65 miles per hour, and you saw the police at the mile marker 6 and slowed to 65 miles per hour again. The police did not have a radar device or any device to measure your speed. Why did the police pull you over for speeding? Now, if we think about the mean value theorem, we may think that, well, if we have a slope of a secant line, which is our average velocity over an interval, we could calculate the average velocity over that interval and then realize, well, the slope of the tangent velocity, which would be our instantaneous velocity, has to equal the slope of that secant line. So if our average velocity is over the speed limit, then we know at some point on that interval our instantaneous velocity has to be over the speed limit also. So our interval is from 0 to 4, and the slope of the secant line of this position function would be here, f of 5 minus f of 0. Now, we are converting here all over 1/15 minus 0, because we're taking the distance over time, and our time was in minutes. And so 4 minutes would be 1/15 of an hour. Since the police know the mean value theorem, they knew that the slope of the secant line was 75. So the slope of the tangent line between that time interval also had to be 75 at some point, your instantaneous velocity. So you must have been speeding on that interval. Suppose that f of 0 equals -3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? When we're solving a problem like this, let's try to get an idea of just what it's asking us to find. So it says f of 0 equals -3. So if I draw a graph, we would have a point down here at 0, -3. And it says f prime of x is less than or equal to 5. That's telling me the slope of the tangent line is less than 5 or equal to 5 for all values of x. So it can't increase faster than 5. How large can f of 2 be? Well, if the maximum that this function can increase is 5, which means 5 over 1, it could go up 5 units. So it could go up 1, 2, 3, 4, 5, and over 1. It could possibly get up to 2 because of this statement right here. The maximum the derivative can obtain is a slope of 5. Well, if we continued this process, we could say it could increase another 5 units from 2. So let's see, do I have 1, 2, 3, 4, 5? So it could go up 5, 1, 2, 3, 4, 5, and over 1 again. So let's see what that value is. That would be 2, 3, 4, 5, 6, 7. So the maximum f of 2 can equal is 7. That's the maximum it could possibly be. So that's just thinking through this problem graphically. We could also solve this equation algebraically. Since f is differentiable everywhere and it is continuous, we could apply the mean value theorem on the interval 0 to 2. And then there exists a number c such that f of 2 minus f of 0 equals f prime of c times 2 minus 0. Now, something it doesn't say that it should have in this problem, it should have said f is continuous and differentiable on this interval. So if we plug in our values, and now we should be able to find our f prime of c has to be less than or equal to 5. And we know f of 2 must be less than or equal to 7.